Hi, everyone, and welcome to our second session with Mark Powell. If you haven't watched the first one, make sure you watch the replay now. And well, I don't mean now, make sure you watch replay at some stage, because it was a wonderful kind of introduction and lean way into this session. Everyone, please remember to keep this interactive, ask questions underneath this video, talk to one another. Write comments, reply to other comments, just keep this interactive, and don't forget to share this workshop with your followers and your friends on social media, and keep notes, write down important messages, important points. This session is going to be very, very practical and very useful. Mark, why don't you introduce yourself and tell us a little bit about what this workshop is going to be about?
Okay, thanks, Alex. As a start, met Alex on LinkedIn. I don't participate in LinkedIn anymore because I just don't have the time. LinkedIn can take a lot of your time, and I've been busy, which is great. I have had a very, very good career. In fact, I was able to change from working from employers to consulting in academia back when I was 47 years old. It was so lucrative that I was able to do that, did a lot of exciting work. And the three hallmarks of that career when I was working for other people, one of them I don't do quite so much anymore, but one was that I rescued a lot of doomed projects. Now, when I say doomed projects, we're talking about projects that the customer management, they thought it was a lost cause. It wasn't necessarily doomed, else I wouldn't have rescued it. But everybody believed it was when they assigned it to me. And of course, typically, I was always the thing that inspires me and that I'm passionate about is I love working in very, very technical areas. And I love working on technical problems that are just real serious challenges, things that are very, very difficult to do, problems that a lot of people consider to be impossible. And I've been assigned a lot of those in my career, and I continue to do that. I get to do a lot of that in my consulting work. But my career, as I say, was so lucrative at the tender age of 47, I was able to move directly to consulting and also to teaching in academia. So the three hallmarks are really that I've rescued doomed projects, I have solved impossible problems that people had given up on and assumed were impossible. And the other thing is I share all this information. In fact, these two sessions in Risk Awareness Week, this particular session is about using Monte Carlo and decisions using Monte Carlo, because the only reason we do Monte Carlo is to make decisions. And most of you know, Monte Carlo is kind of considered the gold standard tool to use in risk management. So I want to explain Monte Carlo, and I've come up with a technique where we really can solve that problem. And I'm going to share it with you, that where you worry about the number of samples that you use. But I want to go ahead and give you, I teach. That's what I'm getting at. I'm inspired by sharing how to do all of these things. And that's the reason why I do this. Hopefully you'll detect some of my passion in this presentation for teaching and sharing this information. But I want to tell you a little bit about one project that I did rescue. And I've been working at this company for a couple of months when they came and gave me this project. I was assigned to be the chief systems engineer. Now, the chief systems engineer, if you're not familiar with that term, is responsible for the entire technical management, all of the technical work. Now, we also had on that project a project manager who was pretty much a figurehead, didn't do anything, so I had to pretty much become the de facto project manager. I had to do that work as well. But anyway, I was given this project. I considered it a medium-sized project. It was $182 million. It was a start from scratch project. We had to do a design, we had to build some facilities, and there was a long period of operations for this particular project. As I said, the budget was $182 million. We had a 15-year period of performance. And of course, as I do with all projects, and this is how I rescue projects, I apply science, I apply engineering, I apply good math, and just a ton of critical thinking. First thing I did was develop 43 coordinated management plans. And if you're familiar with me at all, you'll know that I'm always telling people that every management plan is a risk management plan. Therefore, all those things that every project experiences, those uncertain future outcomes that you have to plan for. And so you have a system engineering management plan, configuration management plan, system integration verification plan, reliability management plan, just a bunch of them. So we developed 43 that were all coordinated, that explained what everybody on the project was supposed to do, the procedures for doing their job. And we literally had 150 people carrying around one or more plans that applied to their particular job on this project, because it told them how to do their job and how to do it correctly. So that was one of the first things. But after about a month on the job, I found out that this particular project was a do-over, and that the previous contractor that had attempted the project had defaulted on the project. Two aspects of this project were new to me. One was that the milestones were fine and enforceable. If the customer did not approve us going forward on a milestone, we were fined $10,000 per day. Well, the previous contractor had gotten into the realm of missing milestones. They did not make the customer happy, and so they were fined $10,000 a day. So they defaulted on a contract, sued the customer to try and get the fine money back. And of course, the customer sued them. There were about 4 or 5 lawsuits going on. It was really an ugly scene. And of course, what we were left with, the original contractor had $554 million for this particular job. And they had 19 years, and they burned 4 of those years. And they had burned all but $182 million, which is why we got $182 million, around 30% of what the original budget was for this project. So everybody assumed, the customer, everybody assumed this was a lost cause. It was literally a lost cause. The other contractor defaulted and failed. There was no money left for all intents and purposes. Well, there's an aphorism I want to share with you, and it's true, and this is a perfect example of it. The first 5% of your effort determines 95% of the overall project cost. And in this particular case, the other aspect that was interesting, besides the fine enforceable milestones, was that all of our project records had to be made available to the public on demand, 24 hours a day, 365 days a year. That's interesting. Most people are not familiar with working on projects where all of their records are available for public scrutiny. So that was an interesting process. But we developed plans and processes such that our project records were suitable for public viewing. But in any event, I only worked on this project. It had 15 years for the period of performance. I only worked on it for about 2 years. During those 2 years, as I said, I started out with all of those plans, all coordinated, all put together, explaining how people should do their jobs, the processes and procedures. But the one thing that I did that was good was that I got us through all of the enforceable milestones, except for the very last one, which was completion of the project. I got us through all of those ahead of schedule. In fact, as a result, I was rewarded very generously. Many, many people on my team were rewarded very generously as well. And in fact, because of those rewards, that's one of the reasons why I was financially able to go into consulting. One thing I always tell people, if somebody comes up and asks me if they should go into consulting, first question I ask them is, well, do you need the money to live? And if their answer is yes, I said, don't go into consulting. You're gonna appear needy, and you won't get work. I said, but if you don't need money to live, you can make a fortune. And I've been very successful as a consultant. I've got to work some really exciting things. I've worked for, oh Lord, my background is space and defense primarily, but I've worked in environmental remediation. I have worked in medical devices. I've worked in beer. I've worked in wind farms. Had a consulting contract for a long time as a consultant to McKinsey & Company. So I've done a lot of really exciting things. In fact, it's been more exciting, which is one of the reasons why I went to consulting, so I could pick and choose the fun things to do. And for me, the fun things are those technical challenges. Well, this project I left it after about a year and a half, 2 years. All we had left after getting through those fine enforceable milestones ahead of schedule was a little bit of critical design, about a year of construction, and then several years of operations. For me, operations and construction don't provide a lot of intellectual stimulation, and I need a lot of intellectual stimulation. And I have, in fact, I worked for TRW, which was a great company, had a great job working on space shuttle until after the fifth flight. After the fifth flight, space shuttle was operational. And I hate to say it, what was exciting turned very, very boring. And I left TRW. I've left several jobs because I like to work the exciting things. I don't like to just do menial labor, which is what space shuttle. It's hard for somebody to believe that the space shuttle was ever menial labor, but it was menial labor to me. So likewise, I was going to leave this project regardless, but I was able to go into consulting because financially didn't need the money to live, which was great. But that's an example of how good my career was. Well, I had to read about it in the paper later, how this project turned out. And I mean, literally in the newspaper, I had to read about it. And what I read about it, three things stood out. One, the project was a success. And two, they came in 2 years ahead of schedule. I anticipated that they should. I didn't know if they would without me at the helm. Clearly, I set things up well enough to where it continued, which goes back to the first 5% of your effort, determines 95% of how it's going to go on the project. That's a very, very important truism. The third thing that was really astonishing is we had a budget of $182 million. We came in at $34 million. Now, that's a cost savings of $148 million out of $182 million budgeted. But even more so, it is a cost savings of $520 million out of the original budget that was given to the original contractor. This is what I do. This is how I rescue doomed projects. This is how, and there were a lot of impossible problems along the way in that as well that we had to solve. This is what I do. And I have done it, like I say, for McKinsey and Company and a herd of companies since I went into consulting in academia. So that's kind of the story I wanted to tell you. Several other things. I advise you strongly to look at Risk Awareness Week, the presentations I made on the state of the art on quantitative risk assessment. The first one, I made 3 last year. The first one really discusses the philosophy and concepts in risk and risk management to help people understand what they're really doing. But there's a lot of confusion as to what actually goes on. A lot of it is due to standards and other things. But I would advise looking at that because it'll set up the context for both my other presentation, which had to do with how to build a risk matrix from scratch using science and math, which very few people do these days. And this presentation, which is about using that gold standard for risk and risk assessment, which is the Monte Carlo method. So this is where I am today. I'd advise looking at the Risk Awareness Week 2019. And I guess I'm ready to go, Alex, to get started on the presentation.
Sounds very good. Please start the presentation. Don't forget to ask questions, write comments underneath this video. And I wish I could say you can find Mark on LinkedIn, but he's no longer active on LinkedIn because we had so much fun embarrassing risk managers who are doing flawed risk management one practices. So I'm very excited about this presentation. Monte Carlo simulations is truly the gold standard of trying to quantify uncertainty and trying to make decisions under uncertainty. But it's not without its problems, and it's not without its challenges. And one of the challenges Mark will talk about today because it has been solved, and this is something that Mark will share with us.
All right, thanks, Alex. Yeah, the title of the presentation, Decisions Using Monte Carlo. Everything we do, if you're familiar with Alex at all, you know Alex will explain to you that all of risk management is about making decisions, and the tools that we use, like Monte Carlo, are also about making decisions. That's what it's all about. And you'll see the subtitle, using more samples may not be better. That is one of the dilemmas we're always faced. Have we used enough samples in our Monte Carlo to get a good answer? And of course, when I was on LinkedIn, there were a lot of discussions, and there were a lot of discussions that indicated that a lot of people didn't really understand Monte Carlo very well. And some of those comments came from builders of Monte Carlo tools, which was really interesting. So I'm going to go through and explain Monte Carlo and explain a technique where you no longer need to worry about how many samples you use. So this is a revelation of something that everybody who does Monte Carlo can use very, very quickly and very easily. So let's get started. Let me see here. As I mentioned, Monte Carlo is always used for decision making. All of risk management, for that matter, is used for decision making as well. Monte Carlo is just a tool we use in risk management. And that's the only reason that we do a Monte Carlo, is to help get a decision made. And every decision that's ever been made in the past 4.5 billion years, within 250,000 miles of the center of the earth, was always based on a measure of risk. If you learn about decision theory, decision analysis, it's always based on a measure of risk. Now, risk, if you go back to Risk Awareness Week 2019, especially my first session that I did on the philosophy and the concepts, a risk is really nothing more than an uncertain future outcome, and our measure of that risk is how sure we can be, or the probability that a certain outcome level or above, or outcome level or below, will be realized in the future based on the data that we have. So there's some critical probability value. I'm going to call it P crit, upon which we're going to make a decision. And decisions look something like this. If P true, which we don't know, the probability of that outcome level or above being realized is less than P crit, less than or equal to, we may select alternative value. Else, if P true is greater than P crit, which is the alternate, then we'll select alternative B. Now, the inequalities that you see there, many, many permutations for many, many decisions, but I'm just going to use this as an example for the rest of this presentation because it's a pretty standard type decision scenario. So, especially for risk, because we're looking for a smaller level risk than our P critical. Well, the problem is we don't know what the true value of this probability is. We only have P hat, which is the value we get from our Monte Carlo. In fact, that's all we ever get from a Monte Carlo is an integral value, because probability is an integral. Now, Monte Carlo can be used for other integrals besides probability integrals, but as you know, a probability value is an integral. Even if it's for discrete variables, it's a Riemann integral. Monte Carlo is nothing more than a numerical method to approximate integrals that are too complex to do analytically. Now, this is a surprise to a lot of people because they don't think of Monte Carlo. They'll quite often think of Monte Carlo as Monte Carlo simulation, but the simulation itself has nothing to do with Monte Carlo. Simulation is just basically an integrand. And Monte Carlo is actually giving you an approximate value for the integral. And the reason why we use it is because the integrals that we have in the real world are too complex to do analytically or to even use other numerical methods. But there's a kicker. We never want our computers to produce results that cause us to make bad decisions. Now, as I mentioned earlier, on LinkedIn, there have been a number of discussions where people will write in and say, gosh, what's going on? I did my Monte Carlo twice and I got two different answers. I don't understand. Most people are accustomed to computers giving you the same answer, very, very repetitive. And in fact, if you use a numerical some other integration numerical method besides Monte Carlo, you will get identical answers out to 15, 16 decimal digits. And of course, they won't cause you to make bad decisions if they are within some error band. But we never want, and we never expect our computers to cause us to make bad decisions. And this is a famous quote from Paul Ehrlich: "To err is human, to really foul up takes a computer." First time I saw this actually wasn't from Paul, but it was actually in an S. Harris cartoon in the American Scientist magazine, which was hilarious. To err is human, but to really foul things up, you need a computer. We don't want to foul up with our decisions. We definitely don't want the computer to cause us to foul up with our decisions. I'm going to give you an aside to explain. This numerical method concept may not make any sense to you. You may not be familiar with it. But the computers that we have today are nothing more than fancy 4-function calculators. They have 4 functions: addition, subtraction, multiplication, and division, that are all done in the actual computer hardware. We're talking the electronics. All other math functions, besides those 4, are done in software. And they use only those 4 operations. And of course, they use numerical methods. Now, let me give you an explanation of what numerical methods are. I'll mention to you also, there are more primitive computers than what everybody uses. I've actually used computers where they only had the plus operation and a bunch of logic operations. And you had to actually, in software, create subtraction. You had to create multiplication and division. So I've worked on computers that were that simple, which kind of belies my age. For an example, the function sine of x, you expect to get a perfect answer every time you evaluate sine of x, that trigonometric function, no matter what x is. Well, the way it's actually implemented in a computer, it has to be done in software, because sine of x is not one of those 4 mathematical functions. And the way it's done in a computer is we use the Maclaurin series. You can expand sine of x in an infinite Maclaurin series. And I showed you the first 4 terms of that series and how it compacts into a summation notation for values of x less than 1. And of course, with our trigonometric functions, we have our identities where we can go to the different quadrants and use them for different quadrants to get the full circle for the value 0 to 2 pi for x. So we have a Maclaurin series, and that Maclaurin series, if you use all of the terms, all the infinity of terms, you get a perfect answer. However, if you truncate the series to n+1 terms, you're going to have an error, and you're going to have a remainder. Now, the beauty of the Maclaurin series is the remainder term after those n+1 terms. You see k starts with 0 up to n, so you have n+1. The remainder term has a nice algebraic formula that's bounded. In fact, the remainder term is always going to be less than or equal to x to the n+1, or the absolute value of that, divided by n+1 factorial. Well, of course, x, the max x could be is 1, so it's going to be less than or equal to 1 over n+1 factorial. So we actually can bound that. Now, why is that useful? Because in our computers, we use a standard size word. The IEEE 754 word, single precision, gives us 15 decimal digits. So if we can find the number of terms that reduces that remainder to less than 10 to the minus 16th, we're going to get exactly the same answer on any computer for the operation of sine of x. And it turns out all it takes is 10 terms to give us 15 decimal digits, to converge to 15 decimal digits that are exactly the same no matter which computer. And that's what we're accustomed to. But a numerical method is how we get any of the transcendental functions, any of the trigonometric functions, the exponentials, the logarithms, any function you can come up with, gamma functions, which of course the factorial is, all of them use just those 4 functions. They use numerical methods to get them. Now, there's a reason why I mentioned it. I mentioned a minute ago on the previous slide that Monte Carlo is a numerical method. And it is. And it turns that the number of series terms for Monte Carlo is the number of samples that we use. And of course, when the number of samples, this is little math that you can do, it's easy to show that when the number of samples for any Monte Carlo is infinity, your MC answer is perfect, out to as many digits as you want to go to. No error whatsoever. However, if we truncate to less than an infinite number of samples, there is, unlike for the Maclaurin series for the sine function and all the other numerical methods we use to implement all the rest of the functions, besides the 4 in a computer, there's no known remainder term formula for Monte Carlo, and there never will be. Nobody's ever been able to come up with it. And of course, the challenge with Monte Carlo is how many samples do you need, such that you don't get different answers each time. Well, it's impossible to bound the errors for an MC approximation based on the number of samples. There's no way to do it. And these inherent numerical method errors that we cannot know cause bad decisions every day. And I'll show you how that can happen as well. And I will show you that we no longer have to have bad decisions caused by errors in Monte Carlo. This is what I'm going to show you. Well, before I really get into that, to give you a feel, I want to explain how Monte Carlo actually works. And suppose your daughter came in one day with a big maple leaf and asked you how big it was. Okay, so Mommy, Daddy, how big is this leaf? Well, this is an elaboration of an example in an excellent article by Brian Hayes in the American Scientist. The title of it was Quasi-Random Ramblings. And the article, the subject of the article is how Monte Carlo, the differences in Monte Carlo using either a pseudo-random number generator to get your samples or a quasi-random number generator to get samples. But he explains Monte Carlo with this leaf example. And I want to use this and elaborate a little bit because it really makes you understand. Now, clearly, that leaf, your daughter is asking you about the area of that leaf, which is an integral, which of course might be suitable for Monte Carlo. But one thing that we could do if we're engineers and scientists, we could actually come up with a function for each line segment. We'd have to fit it. We'd have to take measured points, measure a whole bunch of points along each segment, and fit some curve to fit some, say, a second order polynomial for each segment. We could probably get away with doing that. And that would give us a whole bunch of different functions, analytical functions, that we could then actually integrate analytically using all those different functions. Now, as you can imagine, this process, if you wanted to use an analytic approach or an approximate analytical, very, very accurate approximate analytic approach, might take you 2 or 3 days to do that for your daughter. And it still have some errors. They'd be tiny due to the fitting process because you're going to be using some kind of least squares fit on that curve. Pretty doggone good. It's not perfect, of course. It'll have some small errors because you are using a fitting process as another numerical method. And all numerical methods have errors. Well, a grid might be easier. Suppose you had a 10-inch by 10-inch light table and a 10-inch by 10-inch grid with 1 square inch pixels on it, where the dots represent the center of each of those 100 pixels. You get 100 square inches on that grid. You could put the maple leaf on it. Okay. You could count the number of pixels that the leaf touches or contains. Okay. You could count those numbers, divide by the total number of pixels. We had 48 red pixels, pixels that were on the leaf. So our approximate area is 48 square inches. Basically, we have M equals 48 inside the limits of integration. M represents the number of terms, the number of samples that we found to be inside the limits of integration, which is the leaf, of course. But of course, the whole light table is 100 square inches. So we get 48 square inches using this. We have an answer for our daughter. Well, we might be able to use random pixels instead of a grid. I know that sounds crazy, but let's see how it works. I picked the same light table, but I didn't bother to put the boxes around the pixel centers, but I've got 100 random pixel centers on there. Each one represents 1 square inch, and it's over the same total area of 100 square inches. So let's put the leaf on this light table with these pixels. Well, it turns out we got 48 red pixel centers and got 48 square inches. That was awfully convenient. I'm going to be perfectly honest with you. You should be sitting there saying, he shouldn't have got the exact same answer, and I didn't think I was going to get the exact same answer either. I got M equals 48. It was a fluke, but it was particularly convenient, and and I thought about, no, I got to go get a different set of samples to where the number doesn't come out the same to show that it's just approximate. But I thought since this actually happened in real life, I'd go ahead and give it to you. And it is particularly convenient. So what we found out is this is how Monte Carlo works. It's simply a numerical method to approximate a definite integral. Now, the integral that we just did, if we'd done it analytically, we would have used all of those functions, and the integral was simply a uniform distribution or uniform points for the grids. Would have been fairly simple. However, what we found is it makes little difference, especially with those two examples, whether you used a fixed grid or random samples. That's amazing. That is just absolutely amazing. You get away with that. This method that we call Monte Carlo was used as early as the 1600s. It's been around for several hundred years. And it got the name MC, of course, on the Manhattan Project. Everybody knows that story because I forget if it was Lim or who it was. We had an uncle that loved the city of Monte Carlo and gambling there. Computers have made it extremely popular because before computers, the samples had to be gotten from somewhere, usually from experimentation, which took a long time, and you didn't have large numbers of samples. So computers have really made it popular. Of course, to err is human, but to really foul up takes a computer. So we can foul up using Monte Carlo. Now, big question is, where do we get our samples for the integral? There are a number of sources. The first one, obviously, we saw is you can use a grid. And if you have an n-dimensional problem, it turns out that with our leaf problem, we have a two-dimensional problem. We have a two-dimensional grid. You can have an n-dimensional grid that you can generate to use your samples. You can use pseudo-random number generators. That's what we used before for the other example with the leaf. Pseudo-random number generators are only available, they're available for a large range of named recognized distributions, anagrams, and there are essentially infinite number of unique sequences possible. And also the length of the sequences, for all intents and purposes, infinite. It's not. There is a repeat, but nobody's ever going to do trillions and trillions and trillions of Monte Carlo samples. So for practical purposes, the sequence for our uses are going to be simply infinite. And there's essentially an infinite number of unique different sequences possible using pseudo-random number generators. Quasi-random number generators, many of you may not have heard. They have some different characteristics. And I'd recommend you look at the Brian Hayes article. It talks about it a lot. And of course, the subject of the article is very, very closely related to what I'm going to present to you today. These aren't built into any code. You pretty much have to code them. The algorithms are not complicated, pretty easy to code. And I only know of two recognized distributions, but you can, for any of the named recognized distributions, do additional transforms to transform the quasi-random numbers into those. There are Markov chain samplers, which will give you random numbers as well. You're going to have to code them yourself, but they're surprisingly easy to code. It's really surprising. But the Markov chain samplers have some interesting characteristics. They'll work for any integral you can formulate, not just those recognized distributions that you're used to using. And probably if you use a Monte Carlo tool, you have to pick. You're limited to picking from the distributions in that tool. Well, in the real world, quite often we have integrans that have distributions that are not anywhere, not in any tool. Also, Markov chain samplers have been used for extremely high dimensional problems. There have been 20,000 correlated random variables used with Markov chains of sample. So in the literature. So they do, however, require some manual tuning of Markov chains, which is a learned art, I will tell you. Or you could use noise from nature. Military agencies for years, if they want an unbreakable code, they select noise from nature. They'll put up an antenna and take samples of noise in periodic intervals, and you can't get a sequence that you can repeat. For a pseudo-random number generator, a quasi-random number generator, or a Markov chain sampler, you can back out. It takes a lot of work, but you can back out what the sequence is, and therefore you can predict the future of it. Noise you can't. So you could use noise from nature. There's 5 different ways to get sources, samples. All of these have infinite numbers of unique sequences that you can use of samples. And I want to caveat this, they're only near infinite for PRNGs. QRNG is a Markov chain, but for practical purposes, you may as well consider them infinite. So we get a lot of different ways to get samples. The ones that we use the most are PRNGs, because that's what most of our tools have built in. Let's go back to our leaf. Our MC answer is sensitive to where we put that leaf on the light table. If you rotate that leaf right 90 degrees, about the center of the leaf, all of a sudden we get M is 47 pixels, which gives us an answer of 47 square inches. If we rotate it a full 180, well, we get M is equal to 46 red pixels. So we get 46 square inches. And if we rotate it a full 270 degrees, we get 45 pixels. M is equal to 45 pixels, we get 45. Now, of course, those are just 4. You could rotate it any angle, and who knows what answers that you would get. So all of a sudden here, we thought we had 48 inches as an answer. Now we've got somewhere between 45 and 48 that might be the true answer. We just don't know. This may be good enough for your daughter or government work, but most of the problems, the decision problems, we need a little bit more accuracy in this. It's also sensitive when you use random pixel centers. Now this is the first one. The first set of random samples that we got 48 square inches given that, which was, like I said, a very serendipitous answer considering the example that I was giving. But it may be sensitive. We know that to grid placement, you could take that particular set of samples and place the leaf. We could go through that same exercise and get different answers, but also to different sets of random samples. So we get a second set of random samples, and this time we get 49 red pixels. M equals 49. We get 49 square inches. That's pretty close to 48. We take another set of 100 new random pixel centers. This time we get 43 red ones. Oops, that's quite a bit different from 48. And we'll do it a fourth time. Another 100, and we get 54. Now our possible answers range between 43 and 54. This is exactly what some of the people on LinkedIn have seen, and it drives them crazy because they're not used to their computer giving them different answers. Now, on LinkedIn, we have had some developers of Monte Carlo tools chime in and say, there's a solution to this. Just fix the seed in your pseudo-random number generator. All that does is fix the error. It doesn't give you a field. Another one of our speakers in Risk Awareness Week, Personal Conversations, both last year and this year, has told me that, well, what he does is he runs his Monte Carlo 3 or 4 times and sees what the variation is. There's a pretty big variation, 43 to 54. It's 11 percentage points, if you will. And he's told me, hopefully, if he watches this, he'll get an idea to improve this tool that he has. But anyway, we see variation in the answers due to each possible random set. Well, the message here is, unlike the Maclaurin series, the truncated Maclaurin series for sine effects and all the rest of the transcendental functions that we implement in software and computer, Monte Carlo as a numerical method is not very accurate. And it's not accurate compared to other numerical methods specifically for integration, Runge, Cut-4, and the others, which do have nice remainder terms, analytical remainder terms that we can bound. Monte Carlo doesn't have that. But of course, we only use Monte Carlo for problems on which you can't use these other numericals or analytical integration. Monte Carlo is sometimes considered a brute force integration method. There are 2 types of errors with Monte Carlo. The first is precision or quantization errors. Clearly, if n is 100, there's only 101 possible answers. You'll have 0, 0.01, 0.02, 0.03, all the way up to 1. 101 possible answers. Okay? If n was equal to 10, you would have 0, you'd have 10%, 20%, 30%, 40%, 50%, 60%, 70%, 80%, 90%, 100%. You'd only have 11 possible answers. That means your answers are quantized in those amounts. Very rarely do we have a nice quantized answer. The other type of errors are convergence errors. This is the variation that we've been seeing in MC answers due to, say, placement of something on the grid, or rotation, or how the grid is formed, or due to the different sequences of random samples that we use. Now for grids, clearly you get variance answers due to just grid placement, not just the shape of the grid or the type of grid. And you could have a hexagonal grid instead of a square grid, and that would give you different answers. Let's talk about quantization errors. The primary idea about quantization errors, they give us a feel for how for how many numbers of samples we need because of the precision of the problem. A lot of problems get quite precise. For example, during launch at Vandenberg, their acceptable risk of loss of life is 3 times 10 to the minus 5. That's 4 zeros and a 3 out there. That is very precise. That's 5 decimal places. The Ares launch abort system misassurance requirement. In other words, they will only accept a 0.27% probability of failure. It's very small. It goes out to 10 to the minus 4. Ideally, you want the quantization errors just like the remainder term. You want it to be so small that it's not going to affect the precision of your answer. You'll still be able to make a decision based on the precision so that you get decent rounding. That requires that quantization error be no more than 10% of the required precision for your decision. For example, the Ares launch abort system, that turns out the precision needed is 1/100 of 1%, or 10 to the minus 4. You want your quantization error to be an order of magnitude smaller than 10 to the minus 3. That means that you need 100,000 samples to just reduce the quantization error such that it'll round nicely to the precision for the question. Okay, that's where quantization comes in. Convergence errors, however. MC answers converge, just like the series for sine, converge to k decimal digits when the same k decimal digits appear in all MC answers, regardless of the sequence or the grid used. Okay, just like sine, when we use 10 terms, converges to 15 decimal digits. No matter which computer you run it on, you're going to get the exact same 15. Well, a Monte Carlo answer would converge to, say, 3 decimal digits. That regardless of which of the infinite set of sequences you used to compute that answer, you would get the same 3 decimal digits. That's what we mean by convergence. And of course, that was the subject of Brian Hayes' article, Convergence of using a pseudo-random number generator versus a quasi-random number generator to get your samples. Interesting problem. Convergence errors are much larger than quantization errors. Now, typically, unlike the other speaker on Risk Awareness Week, most of the time we only run one Monte Carlo. Monte Carlo can be quite expensive and quite compute intensive. I worked on some problems where it took 3 days of computer time to produce a single sample. We've worked, I know one time we had 128 different computers running that had to run for about a day and a half to give us each one Monte Carlo sample. So we had 128 Monte Carlo samples, but it took a day and a half to get those, and only because we were using 128 different computers. So typically we only do it once and make our decision. The question is, and it's always there, how many samples are needed to get the k digits of convergence? And of course, the number of digits that we need has to do with the precision of the answer of p-crit to make our decision. There are a lot of articles in the literature that talk about, well, more samples reduces the relative standard error of the answers. If you don't know what a standard error is, a standard error is a measure of dispersion of the answers, very similar to a standard deviation. A little different. In some cases, it's coincidental with a standard deviation. But there is no formula for any sort of absolute bound on any Monte Carlo error, nor even a bound on the standard error. So we don't know. We do know relatively that if you go increase the number of your samples, the standard error reduces. But we don't, and we know approximately the factor of reduction. But since we don't know what it is to begin with, we don't know if that solved our problem. So pretty much the only advice that we've got is we can increase the number of samples, which reduces the relative standard error. It's about the best advice. Is it good advice? Not necessarily. So how big can Monte Carlo errors be? Well, I've wondered. You know, I've been working, first Monte Carlo I did was in 1969. Of course, I didn't know what I was doing. I was following somebody's instructions. And I didn't understand the full details. I thought, hey, this is cool. I can use this in a lot of things. But I had no idea how big Monte Carlo errors could be. And so one way to find out is to look. So what I did is I repeated a Monte Carlo 1.2 million times. I thought 1.2 million is good sampling. I used 19 different integrals. This is the way you validate things. You use integrals with known answers that you know the answer to. I used 19 different ones. And I looked at 4 different numbers of samples, 100, 1,000, 10,000, and 100,000 for each of the 19, and 1.2 million for each of those. I use a pseudo-random number generator in R. If you're not familiar with R, it is free. It is a very, very powerful computing language, as well as for nothing else. I mean, it's great to download. It's free. It is extremely well managed. It's as good as anything else out there, I'll be perfectly honest with you. And the random number generator they use is the Mersenne Twister, which is the gold standard in random number generators. It has an incredibly long sequence, and any tool maker that does Monte Carlo wants to use the Mersenne Twister. So I used R. It's a good one. It's a good example. And of course, R is very, very easy to code in. It took 67 hours to repeat those 1.2 million Monte Carlo runs for 19 different integrals with 4 different numbers of samples. So that means that the pseudo-random seeds that the computer picks were picked over that 60. Now, is that representative? It should be. They could have happened at any time. And the way computers generate those seeds is they have a complex formula that actually uses the time out to several significant digits, milliseconds or microseconds, way out there. They use the time in the computer as the factor. So each one of these sequences was different and unique, and they happened sometime during a 67-hour period. So the point is, this gives me an idea how big Monte Carlo errors can be. And what I did was I collected for each one of those integrals, for each number of samples, the minimum and maximum MC answers over that 1.2 million MC runs. And the answer, pretty damn big. Okay, let's look at it. Now, this is going to be an eye chart for you, but this is the table that of all of the minimums and maximums. Over here on the far right, you're going to see these are the true integral values. And I used numbers starting at 10 to the minus 5, 10 to the minus 4, all the way up to 1%, 10 to the minus 2, then 5%, then 10%. Then I went in deciles all the way up to 90. Then I went to 95, 99, then 99.9, and 99.999. Okay, 5 nines. And the reason why, is I have seen problems and dealt with problems with all of these numbers being a p-crit. Okay, but interestingly enough, if you look over here to the right, where the true answer is 10 to the minus 5, out of those 1.2 million values, we only got 2 different values. We got zeros and we got 0.01. Of course, that's the quantized. We have no idea how many of those were good or bad. If the true answer, if p-crit was equal to 10 to the minus 5, obviously only those that came in at 0 would have given us a good decision. But that's interesting. If you look over to 100,000 samples, out of those 1.2 million runs, we only got 9 different answers. And guess what? 7 of them would have given us a bad decision if we selected alternative A. So that's kind of interesting. And clearly you see the quantization that I was talking about. We got 2 digits of quantization within, 3 with 1,000, 4 with 10,000, 5 with 100,000. But the answers are really, really interesting. And I want to show you where the errors are the worst, which is interesting. That's when the true value of the integral is at 50%. We got answers as low as 27% and as high as 75%. Now, one thing I want to mention to you is anybody can reproduce what I just did. It's very, very easy. In fact, I've done it multiple times, and the answers are all within 1 digit when I've done it multiple times at different 67-hour periods or with different numbers of samples. They're all real close. In fact, the first time I ran it, I only used 5,000 unique sets. And actually, these bands were smaller. No surprise. When I went to 1.2 million, which is a huge factor over that, they actually expanded quite a bit. That meant that these actually happened, these spans, as you say. So when the true value of the integral is 50%, you might, for Monte Carlo, get anything from 27% to 75%. That's a large error if you use 100 samples. Even if you get over to 100,000 samples, it's plus and minus 0.8%, a little less than 1%. So those are pretty big. As I said, pretty damn big. Let me show you some other curious things. Let's suppose our p-crit for our decision was 30%. And let's suppose our Monte Carlo gave us a 0.26 using 100 samples. Now, right off the bat, that's lower than 30%, so we might select alternative A. Sounds very reasonable. 0.26 is quite a bit smaller than 30%, 26% smaller quite. But let's see what we could have gotten. If it was the minimum value we might have observed, could have been 0.26, 0.27. The true answer might have been 50%. Okay, that would have been a big mistake to select alternative A. Also, it could have been the maximum answer for a true value of the integral of 10%. There we would have been safe. But the fact of the matter is you don't know what the true answer is. With that answer from Monte Carlo using 100 samples of 0.26, it could be anywhere from 10% to 50%. That doesn't help you make your decision for 30%. Now, this table is only with 1.2 million unique sets of PRNG generated samples. What if we went to 1 billion unique sets? These bounds would probably get even larger. But the problem is you don't know what you got. You could perhaps do some statistics and say, well, yeah, it should be somewhere in the middle. That's nice. But typically you only make one Monte Carlo run. And if your p-crit was 30% and you got that Monte Carlo at 0.26, what's your risk of making a bad decision? It might be pretty large. This is the problem. And this is the reason why I told you bad decisions get made every day. Now, when I do Monte Carlos, I rarely do less than 100,000 samples. Quite often I do 300, 400,000. How many of you have done a Monte Carlo and made an important decision just using 100 samples or less? I've actually seen some important decisions made. It takes 3 or 4 days to generate a single sample. The kicker is we do not want our Monte Carlo answers causing bad decisions. There's enough things to cause bad decisions. We don't want our computer to cause us to foul up. Will more samples help? Well, that's kind of the conventional wisdom that it will. Well, suppose for your particular problem that the true value of the integral is exactly 0.7, 70%. And suppose using a Monte Carlo with just 10 samples, you got m equals 7 and a p-hat, Monte Carlo answer of 0.7. Obviously, there is no error in your Monte Carlo result that you got. And you can see how that could happen. If you went to 100,000 samples, it turns out that the only Monte Carlo answer that you could possibly get where there wouldn't be an increase in the error would be m equals 70,000. Now, how many times do you think you're going to get exactly 70,000 if you use 100,000 samples and repeat that multiple times? Not very often, okay? You're going to get a whole bunch of answers that may be between 70,000 and 169,900. They all increase the error. So the question is, will more samples help? Some cases, more samples can only hurt you. But the kicker is we only use Monte Carlo because we don't know the true value of the integral. We need to approximate it. So the question then comes back to the same question that everybody has. How many samples do we need to keep Monte Carlo from causing us to make a bad decision? That's really the answer. People will say, how many samples do I need to converge? How many samples do I need for this, that, or the other? But the real question is, how many samples do you need to keep MC from causing a bad decision? All right. I've got a risk-based solution for you. Let's look at that leaf again. That's our very first set of 100 random samples. There is indeed a true value for the area of that leaf, for P true. We don't know what it is, but there is a true value. If we get our samples, and before we put the leaf on there, each sample point has a probability of P true of being on the leaf. In other words, inside the limits of integration. And it didn't make a difference the orientation of the leaf. It doesn't make any difference whether it's rotated, whether it's shifted. Each sample point has a probability of P true being on that leaf when you finally put the leaf on there. What that means is each sample is thus a Bernoulli sample. If you're not familiar with a Bernoulli distribution, it's like a coin. Okay, coin flip. A Bernoulli sample has two outcomes. In this particular case, inside the limits of integration or outside the limits of integration. And there is a probability that it will be inside. Flip of a coin is another example of a Bernoulli sample. If you have a fair coin, there's a 50% probability you'll get heads when you flip it. If it's an unfair coin, let's say it's the 60% probability of getting heads, that will be the probability that you will get heads. But you have two outcomes. So each sample that we have, that we generate for doing Monte Carlo, is nothing but a Bernoulli sample. And it has the following uncertainty distribution. Now you'll notice I use the vector x. The reason why is what we're solving there is a two-dimensional integration problem. We have both x and y coordinates, which require two samples that actually give us one sample. It's either inside or outside. So you have n-dimensional samples. If you have an n-dimensional problem, each sample is n-dimensional, which means you may have n times the total number of samples to generate, which takes computation time. Let's look at our decision again. If P true is less than or equal to P crit, then we select alternative A. Else P true is greater than P crit, and we select alternative B. This, like I said, this is just an example decision. We're going to run with this one. Our risk of making a bad decision because of MC can be calculated. The probability that P true is greater than P crit, when our Monte Carlo answer said that it's less, is the risk of making a bad decision. Likewise, the probability that P true is actually less than P crit, given that our Monte Carlo answer was greater than P crit. Now, and of course, P hat is M divided by N, the number of samples inside the limits of integration divided by N. Well, what we need is an uncertainty distribution for P true, given the Monte Carlo results. Well, we can find one. We know that, for example, if we got an MC result M, we had M inside the limits of integration using N samples. Well, there's a simple binomial probability for getting that M given P true. It's just a simple binomial probability. So the probability that we would get M given we used N samples of P true is just simply that binomial probability. Real easy. If we used an objective model for what our uncertainty is about P true, and there are three ways to do that. I discussed them in last year's Risk Awareness Week 2019, one of my presentations, because they're very, very useful. Three independent methods. In fact, one of our other speakers on Risk Awareness Week's father developed one of them in 1961. They've been around a long time. For a Bernoulli problem, it turns out that it's a simple beta distribution. Most of you are familiar with the beta distribution. It's for an interval. And this is the standard beta, so it goes for an interval between 0 and 1. P true goes between 0 and 1. And it uses the two shape parameter values of 1/2 and 1/2. Now, of course, to get the objective uncertainty model for P true, given our Monte Carlo results, it's simply the product of those two distributions, which turns out to be very, very nicely that beta distribution. P true given as one of the parameters M plus 1/2, which is the Monte Carlo number of samples inside the interval, inside the limits of integration plus 1/2, and N minus N plus 1/2. Very, very easy. Simple calculation. But that is our uncertainty model for P true given our MC results. And we can use that in those equations that I just showed you for calculating the risk of getting a bad decision. Now, we can actually calculate some bounds, risk-based bounds on our MC answers. First off, we have to set for ourselves an acceptable risk of Monte Carlo causing a bad decision. Let's call it RMC. Typically, we want that to be small, okay? But in all practical sense, we're going to have an idea of what, without Monte Carlo, the risk might be for making a bad decision. And whatever the smallest one is, we'd like for our computation risk to be a whole lot lower. So 2 or 3 orders of magnitude lower than that is something that you can use. Now, if you wanted to eliminate it altogether, you could select a risk, since probability always ranges between 0 and 1. You could use 10 to the minus 16, which is just exactly like what we got with sine of x using 10 terms. Our remainder error risk would be less than the 15 digits from the IEEE 754 word, single precision word. Using this distribution we just came up with, this beta distribution, we could compute risk-based bound, a least upper bound on our Monte Carlo answers, and a greatest lower bound by solving these 2 equations. The first one, probability of the P true is less than this hypothetical least upper bound given M and N, and probability of the P true is less than our greatest lower bound is equal to our risk, okay? Now, it turns out these look like pretty horrible equations to solve, but if you want to know what, they're simple quantile functions. R, another reason to use R is R has a built-in for every possible distribution, including the beta distribution, a quantile function. So this is one line of code to get these answers in R. If for no other reason to download R, it's worth it for doing this. So with this least upper bound on our Monte Carlo answer on P true, given our risk of causing a bad decision, and a greatest lower bound, we could set up a very effective decision process using MC answers and never worry about MC errors again, never worry about the number of samples again. Let me go through that process for you. This is very simple. Step 1 is probably what you'd think of. Select your acceptable risk of Monte Carlo causing a bad decision. Now, clearly, as I said, if you select a 10 to the minus 16, that's a pretty small risk. You can do that. I don't think you need to. You want to go a couple of 3 orders of magnitude smaller than the next largest possible risk of causing a bad decision. Lots of things can cause a bad decision. So, but if you don't have a feel for that, maybe use 10 to the minus 9th or 10 to the minus 6th, which are pretty small risks of Monte Carlo causing a bad decision. Very small. And for all intents and purposes, if you're 10 to the minus 6th, you've probably eliminated Monte Carlo from causing you to make a bad decision. Step 2, using a small number of samples N, but as large as is cost effective. Get a Monte Carlo result. Get an M and a p hat. Okay, when I say but as large as cost effective, if it takes 2 minutes to run 1 million samples, run 1 million samples. If it takes 3 days to get a single sample, you might want to get maybe 10. I think 10 is kind of a limited small number, but something that's cost effective. What is cost effective to you? And get your MC answer. Okay, that's step 2. Pretty easy. Let's start with a low number of samples. As I said, if you can get 1 million samples in a couple of minutes, run it. That's not a problem. Use the formula those quantile formula that we just got to compute the lowest upper bound on P true and the greatest lower bound on P true, given our Monte Carlo results. We have 3 alternatives. Okay, and these are mutually exclusive depending on the values of the least upper bound and the greatest lower bound answer. Well, if our lowest upper bound is less than or equal to P crit, in other words, our lowest upper bound is the largest probability that we would expect to get within our range of acceptable risk, making a bad answer. So therefore, all the rest of them are going to be lower. Select alternative A. You've made the decision within your acceptable risk that you set RMC. If the greatest lower bound is greater than p crit, that means that the smallest possible answer within your acceptable risk range is greater than p crit. Select alternative B. You've made a decision within your acceptable risk range. And of course, then the third alternative is where it's in between the greatest lower bound, and the p crit is between the greatest lower bound and the least upper bound. And you got to do one of the following mutually exclusive things. One, well, you can increase the number of samples and iterate at step 2. Something that's even cheaper is increase your acceptable risk and iterate at step 3. Clearly, you don't have to process any more Monte Carlo samples. 3, if you can't afford to do either, Monte Carlo is not going to be useful to you in making a decision. You can't afford to use it. You don't know if you're going to make a bad decision or not. So either, in that point, discard it all and make a seat of the pants decision, or make no decision at all. In any case, if you get through it on the first pass, you know you've made the decision within your acceptable range of risk of MC causing a bad decision at the cheapest possible cost. That's very powerful. Now, the results from using this process that I just described, we no longer worry about quantization or convergence errors. Who cares if the next time you run it, you get a different result? Who cares? You'll be able to calculate your bounds. You only need to run it once. You no longer worry about how many samples to use. You're going to use the smallest number of samples that is reasonable. You're no longer worry about errors in MC results causing a bad decision. You have set your acceptable risk level and you're going to live with it. And you can save a lot of time and resources computing samples and still make extremely good decisions using MC. So this is the process that I developed, and it works great. You have to make a decision. You don't want the computer to foul you up. This is a way to avoid it. You set your risk of the computer fouling you up, and you live with it, and it works. The conclusions. Monte Carlo is extremely useful. Like I said, I've been using it since 1969. But the problem is it can have huge unknowable errors. We don't even know how large they can be, or if you've got a large one, or if you've got a small one. And there's no way to know. They're unknowable. We don't have any formulas we can use to bound them either. That's ugly. The conventional wisdom is more samples are always better, but I showed you a simple example where going to more samples almost guarantees that you increase the error. That doesn't set with conventional wisdom very well. This risk-based bounding of Monte Carlo results gives us a very efficient. This hack can happen very quick with a single run and cost-effective use. Remember, the reason we use Monte Carlo is to make good decisions, not to make bad ones. So the answer is that more samples may not be better. In fact, they may be worse, and they just may not be needed at all. So this is what I wanted to share with you, this technique, and it's very, very easy. I've got a formal paper that's been submitted. It's in the works. We're trying to whittle it down because it's huge, because I've learned a lot of really interesting things. I also have codes available on my website for computing these bounds. They're in R, and like I say, you can download R for free, and you can use this one simple little routine that does some error checking and things. But it's one line of code to give you those bounds, which is really nice. It's hard to believe nobody had discovered this before. My contact information, there's my email address. If you have any questions about this, as I said, the website has got loads of codes, loads of Monte Carlo codes. It has numbers of papers of some really interesting, exciting projects that I've worked on. A lot of impossible problems that were fallow for a long time that I was able to write up in papers that a decision was made like instantly when the results were presented. A lot of tutorials, a lot of seminars, a whole lot of information there. And I'll describe some of the things that I do as well. But anyway, thank you. Any questions, Alex?
Mark, thank you so much for sharing this practical application. And everyone, I hope you heard the message loud and clear. On the website, There will be, as soon as the paper is accepted and published, there will be a more detailed explanation for anyone who's really interested in applying this technique to minimizing the error generated by Monte Carlo, and some sample codes are also available on the website. If you have questions, do write them underneath this video. Write comments, share. I mean, this is one of the more technical workshops during the Risk Awareness Week, and I'm really excited because I know in my team, both of my risk managers, I'll force them to watch the replay, and I'm sure they'll laugh at the moment because they'll be seeing this, because sometimes we do have to make decisions under such small margins of error that this technique will become invaluable. In other cases, decisions that we're trying to make, they're so kind of wide in the assumptions that have been made by the management, then that level of error would be just a huge overkill, and we can just kind of rely on a large number of samples, because we don't really use Monte Carlo for decision making. We just kind of use it to stress test some of the management assumptions, because they choose to not move away from assumptions, something that Mark shared in the 2019 Risk Awareness Week. So thank you very much, Mark. I encourage everyone to watch the replays of 2019 sessions. Mark did 3 sessions last year and 3 workshops, and they were absolutely amazing and practical. And make sure you save this page and share it with your quantitative risk managers, and save this page so you can rewatch it later. And when you are at the crossroads and you want to reduce the error in Monte Carlo, you come to this and you apply the same technique, the same steps that Mark shared. Mark, any final thoughts?
Well, one thing I do want to say, you just said that you sometimes use Monte Carlo not to make decisions, but you use it to stress test assumptions. Well, you're using Monte Carlo to make a decision whether that assumption was good or not. So when we say decisions here, we're not necessarily talking about whether the company invests in something or not necessarily. Sometimes they are, but sometimes you're making decisions about things that you're working on, like whether or not an assumption is valid or not. So the example that you gave was actually decision making again.
I agree. Very true.
So I just want to make sure people realize when I say decisions, it's not necessarily like corporate decisions. It's decisions that we use in our everyday work often as well. So
exactly,
that's pretty much it. This is a real easy technique. I've got the codes on the website. I've been using it for years, and it really helps the decision makers, and it saves a ton of money.
It certainly does in terms of the effort. Because the most important message the 2 important messages that we can summarize from this workshop is the golden standard of risk analysis is not error-free. It's not foolproof. You have to be mindful of that. But then the second one, the solution that people often quote is just use more samples. It's all fun and good until it starts taking you hours and days to simulate properly with more samples. And I mean, I remember when we were simulating, long-term business strategy, and it would take us 24, 48 hours. And sometimes it's fine, but when suddenly we had to present something to the Ministry of Finance, and management started changing some of their assumptions in the model, we suddenly didn't have the time to resimulate. And the key takeaway, the second key takeaway from this workshop is often you don't need to resimulate on large sample sizes, on large number of trials, if you do the proper calculations, if you do the proper math and figure out how much you actually need. often the kind of the minimum acceptable level would be much lower than your intuitive kind of guess as to how many trials to run. So you know, this could save a lot of time and effort in risk analysis. Thank you so much for sharing, Mark. Thanks, everyone.
Oh, you're welcome.
Next risk awareness session.